Oh,
Like, do you not have to calculate another, maybe, like say a new hash in that?
oh, no, this parameter is actually the same.
It all works out to be the same.
Yes, it does. Yeah, yeah, just like here too, works out the same. So, yeah, kind of convenient. Okay, now, I believe I have time for this. Yes, okay, good. So I've covered a number of iterative methods: conjugate gradient, GMRes, MinRes, and now biconjugate gradient. These are just the ones in the non-stationary category. So, so now I'm going to summarize them and say in a way that you can more plainly see what are the differences among them. Now, all right, so I'm going to break them down into two subcategories. So in the first category, we have conjugate gradient. So CG. And then we also have biconjugate gradient, so bi CG. All right. And then in the other category, we have MinRes, so minimum residual method. And then we have GMRes. Okay. Now, first, what kind of matrices can they be applied to? So for conjugate gradient, is only for symmetric positive definite matrices. The biconjugate gradient you can use on any, now by any I mean square and vertical. We're always in that world here, but within that, anything goes with bi CG. MinRes only requires that the matrix is symmetric. Okay, and then for GMRes, again, you can use it with any. Now, I'm going to throw in a third method I haven't really talked about, but it fits in a similar category of conjugate gradient method, and it's called SymLQ. And this, again, requires symmetry. It's basically an alternative to conjugate gradient in the case where you have symmetry, but you've lost positive definiteness. Okay. Now, so this is one difference among them, and that is they're applicable to different classes of matrices. But the difference I really want to focus on is how do they construct solutions? Because one thing they all have in common, all of these are Krylov subspace methods. They all work with a subspace spanned by B, A squared, B, and so forth. They all generate solutions of that form. What we have is each iterate is of this form QK, YK, where QK has columns that span the Krylov subspace. So if all the methods have this in common, how do they differ? How they differ is how do they get YK? And that's why I want to break these down. Actually, if I could use another color, that would be great. But I don't think I Does anyone have a different color marker on them? Right, James? Okay. Okay, I'll go for red. So I want to have a sharp division between the top three methods, BiCG, CG, and SimLQ, and then these two methods, the MinRes and GMS. Okay, and that's all I'll need this one for. Oh, okay. Well, I think someone once told me that I wasn't allowed to use red over IBM, but okay, because these three methods basically use the same approach, and then these two use a very different approach. So the idea is these conjugate gradient-like methods, the goal, all right, so in this column, how do you get YK? The goal is, and this really applies to all three of these methods, that you want orthogonal residuals. Or in the case of biconjugate gradient, you want bi-orthogonal residuals. So what that means is QK transpose B minus A XK, which is QKYK, has to be 0. So, and that results in, actually, yeah, I'm going to leave it like that. Now, BiCG, very similar, is just QK hat transpose B minus A QK YK0. And the condition for CG is the same as that used in SimLQ. It's just that because the matrix is no longer a special positive definite, you have to go about getting the vector YK using a different approach. Okay. Now, what about MinRes and GMRes? The goal for these methods is to minimize the residual, the norm of residual. However, the solution xk is expressed in the same form as before. So I'll go ahead and plug that in here. So B minus A QK YK to norm. Now, this is a least squares problem, a full rank least squares problem. So the way you solve a least squares problem is by normal equations or QR factorization. But I'm going to use normal equations to show the contrast with these guys. So what we have is the normal equations say that here's my matrix for a least squares problem, AQK. So the normal equations say that the residual is normal to the columns of your matrix. So I have a similar dot product, but I have QK transpose A transpose. And now I have my residual, B minus A QK YK. And that has to be 0. So that's what applies here for both MinRes and GMRes. The difference is, well, actually, yeah, there's really no difference whatsoever. It's just that the symmetry buys you some computational savings in actually solving the least squares problem because you're dealing with a much sparser matrix. So if I compare this goal of minimizing the norm of residual to this situation where I'm trying to make a residual orthogonal to some subspace, they're almost exactly the same. The only difference is, in here, I have an A transpose working around. That's it. So that is what sets apart the approaches that these two methods take. Because if you think about the way least squares works, you're trying to make sure that your residuals are orthogonal to a certain subspace, but the subspace that we're orthogonalizing against is, well, okay, so it's A times subspace spanned by all your previous all your previous residuals. So on the other hand, here we just have the residuals themselves. Because counting gradient, the idea is to have some memory to it, that each residual is orthogonal to all previous residuals. That's what this equation is saying. But here, it's orthogonal to A times all previous residuals. Go figure. But what that means is you're going to get a different sequence of iterates. Now, the convergence properties for both kinds of methods are quite good. But especially when you lose symmetry, things go badly one way or another. Either you have some numerical instability, like in the case of ICG, or you have some terrible loss of speed, like in the case of GMRes. But in terms of how you construct your iterates, there's not much difference between them, but what a difference the extra factor of A makes. Okay, so any questions about these non-stationary iterative methods? We're all done with it. Monday, I'm traveling during the morning, but I expect to be back here on campus in plenty of time for class. So we will have class unless something goes really, really wrong with my flights. If that happens, I will let you know. But again, I should be back like well before class. And so we'll spend the rest of the semester talking all about eigenvalues and eigenvectors, my favorite topic.